Jai Hind, welcome to the course Network Analysis and Synthesis, and today we are going to discuss about the waveform symmetry of this course. So, the learning objectives of this course are: what is the importance of study of waveform symmetry, why it is required. So, we will discuss brief about the requirement of waveform symmetry. Then we will discuss in detail about the different types of waveform symmetry, and they are odd symmetry, even symmetry, half wave symmetry and quarter wave symmetry. So, there are 4 types of waveform symmetry that we will discuss in detail, and then in the last we take examples to just find the or discover the or identify the waveform symmetry in a given function signal. So, brief idea about the Fourier series, because waveform symmetry is applicable to a Fourier series. So, first we will discuss the what is Fourier series, what are the different forms of the Fourier series, that we will discuss in brief. For in detail you can refer my earlier video lecture on Fourier series. So, basically Fourier series is representation of a signal over a finite time interval in terms of linear combination of orthogonal function. What is orthogonal function? Suppose there are two functions, say f1x and f2x. If we take the integration of f1x and f2x over a finite time interval, and if the integration is 0, then these two functions f1x and f2x are called orthogonal functions. For example, sin theta and cos theta, they are orthogonal. So, it is a linear combination of orthogonal function. It is applicable to a periodic signal. The signal must be periodic, and it is also called harmonic series. Why it is called harmonic series, we will discuss in detail later on. Then we discuss the existence of Fourier series. If the signal is given and whether we can be able to write down the form of the Fourier series is not, that is decided by some conditions, and these conditions are called Dirichlet conditions. So, they are: the function must be a single valued function, that is it meets the mathematical definition of a function. Then the function has a finite number of discontinuity is a given time period. This is the third. The fourth is the function has finite number of maxima and minima in a time period. And the fourth, the function is absolutely integrable over a one time period. So, this is the mathematically we can define. We take a function f t and integrate over a one time period, say it is from t0 to t0 plus t. Here capital T is the time period of the function. If the integration is coming less than infinity, it means we can have the Fourier series of this function. So, this is very important, this expression is very important. Analytically we can identify whether we may be able to represent the signal in terms of Fourier series or not, that is decided by this expression. Then come to the representation of Fourier series. There are 3 forms of Fourier series: trigonometrical form of Fourier series, exponential form of Fourier series, and cosine of form of Fourier series. So, all these in detail are available in my earlier video lecture on the Fourier series. I am just discussing here in brief. So, take the trigonometrical form of Fourier series. So, any function is periodic and it is satisfying the Dirichlet conditions can be written as linear combination of orthogonal functions, say a0 cos 0 plus b0 sin 0. a0 cos 0 is a0 and b0 sin 0 is 0. So, b0 term is not coming in this expression. Then then we have a1 cos omega 0 t, a2 cos 2 omega 0 t, a3 and so on. Similarly, we can have the b1 sin omega 0 t and bt. So, this expression can be written in this form: f t is equal to a0 plus summation over n is equal to 1 to infinity a n cos n omega 0 t plus Bn sin n omega 0 t. So this is A0 plus F1 t. So this A0 is nothing but this is the DC component of this Ft, and An and Bn. So basically these are the A0, An and Bn. They are called the Fourier coefficients of trigonometrical form of Fourier series. So this we have to derive. So first A0 is given by 1 by t over 0 to t. So function is given, and then we have to integrate over 1 by 1 time period and divided by t. It gives the A0 value. It is the average value or DC component value of the Ft. Then we can have the expression for An is equal to 2 by t 0 to t Ft cos n omega 0 t and dt. And then we have the expression for Vn 2 by t 0 to t Ft sin n omega 0 to d. So derivation of these three expressions have been carried out in detail in lectures on the Fourier series. Here I have just taken the brief idea just to explain the importance of the waveform symmetry. So these three coefficients are required to express any given signal in terms of the Fourier series, especially in the form of the trigonometrical form of Fourier series. So now we come to the waveform symmetry. So if the periodic signal has some symmetry, okay, so then sum of the trigonometrical Fourier series coefficients, that is your A0, An and Bn may become 0, and calculation of the coefficients become simple. So this is the importance of the waveform symmetry. If we may be able to identify the waveform symmetry in a given signal, then sum of the coefficients may be 0. So expression of Fourier trigonometrical form of Fourier series becomes simple if you may be able to identify the waveform symmetry. So basically there are 4 types of waveform symmetry: even or mirror. Why it is called mirror symmetry we will discuss later on. Odd or rotation symmetry, half wave symmetry and quarter wave symmetry. So we will take one by one. Say take the even symmetry, or you can say the mirror symmetry. So a signal Ft is said to have even symmetry if Ft is equal to F minus t. If this condition is satisfied, then the signal has even symmetry. If the function has even symmetry, then this Bn is 0. So there are 3 coefficients A0, An, Bn. So if the function has even symmetry, then Bn is 0. So no need to calculate the Bn. Only A0 and An are to be evaluated. Okay. The sum of or product of 2 or more even function is an even function, and with the addition of a constant given nature of function is still preserved. So this is the property of the even symmetry. So these type of functions are always symmetrical with respect to vertical axis. So this is the vertical axis along which we take the Ft, and along the time axis we take the time. So look at some examples of even symmetry. We can see that Ft is equal to here Ft is equal to F minus t. You can see that here Ft is equal to F minus t. So it is symmetrical about the vertical axis. This is, so these are some examples of even symmetry. So if the signal is given, you can easily identify whether the function has even symmetry or not by discussing this Ft, considering the Ft is equal to F minus t. Cosine function is a good example of even symmetry. So Bn is 0. Now we have to evaluate only A0 and An. So this is the given function Ft is equal to F0t and Fet. So this is the odd part of the function, this is the even part of the function, and if the function is even, so F0 is 0. So, only Ft is equal to Fet. Now, write down the expression for A0t. A0t is 1 by t minus t by 2 minus t by 2 plus t. Basically, it is one time period. If we put here 0, so it is 0 to t. So, only we have to integrate over one time period. So, this is Ft and we find Ft is equal to Fet, and then we can find the value of A0. 2 by t 0 to t by t Fet dt. So, the signal is given, we have to write the mathematical expression of Ft or Fet and then integrate over one time period, we can get the coefficient A0. Similarly, this is the expression for An 2 by t. So, 0 to t minus t by 2, so minus t by 2, so plus t by 2. So, it is one time period Ft cos n omega t. Look at here, this Ft is nothing but it is a even function, this is also a even function. So, it is An is equal to 4 by t 0 to t by t Fet cos n omega t, and Bn is 0. So, this is the expression for An, this is the expression for A0, and by the nature of even symmetry Bn is 0, because it is a, if it is a even function, it is Fn sine function is a odd function. So, multiply even with odd, we get the odd function. So, Bn is 0. So, in the summary, the coefficients A0 may or may not be 0. It can be 0. You have to just check. Coefficient An is given by 4 by t. 4 by t 0 to t by 2, either using this one or this one, and Bn is 0. So, this is the summary of even symmetry. If you may be able to identify the even symmetry for a given signal, we can conclude Bn is 0. We have to calculate only Bn, An and A0. Now, come to the odd symmetry. So, a signal is said to have odd symmetry if Ft is equal to minus F minus t. So, using this expression, we can check whether the given function has odd symmetry or not. So, if the function has odd symmetry, then A0 is 0, An is 0, only Bn is to be evaluated. So, the function is given and you are in a position to identify odd symmetry of that function. So, our function has odd symmetry, then no need to go for the calculation of A0 and An, only you have to evaluate Bn. So, this is the importance of waveform symmetry. The calculation becomes very simple. Then some properties of the odd. So, sum of two or more odd function is always odd. If a constant is added, then the odd nature of the function is removed. These type of functions are always anti-symmetrical with respect to vertical axis. So, if the function has even symmetry, so it has the symmetrical about the vertical axis, whereas if the function has odd symmetry, then it is anti-symmetry. So, this way we can identify whether the given function is having the odd or even. These are the some examples, and the sine function is a very good example of your odd symmetry, having the odd symmetry or odd function. So, this is, we can say the anti-symmetry about the vertical axis, we can see there. So, Ft is equal to minus F minus t. This condition we can check. These 4 examples. So, these are the examples we can understand whether the function has odd symmetry or not. Just check with this expression. So, this is required. So, suppose evaluation of A and Bn is An is 0 and A is 0. So, if this is the expression for A an and it is 0, okay, because it is odd and it is even. The multiplication with odd even is the odd. So Bn is 2 by t minus t by 2, so plus t by 2, one time period ft sin n omega t dt. So this is Bn 4 by t 0 to t by 2 this. So we can easily identify whether the function has either odd symmetry or even symmetry. We can easily identify with the help of the expression ft is equal to minus f minus t in the case of the odd symmetry, and ft is equal to f minus t in case of the even symmetry. But in case of the half wave symmetry, just first we will discuss the definition of a half wave symmetry. So a periodic signal is said to have half wave symmetry if ft is equal to minus ft plus minus t by 2. So this function is neither purely odd nor purely even. In some cases we will discuss those cases later on, and for such functions a0 is 0. So Fourier expansion of such type of periodic signal contains only odd harmonics. So when the n is even, an 0 and bn is also 0. So and when n is equal to odd, so put the write down the expression for an here, and then change the variables from t to t plus t by 2 in the second integral, we get this. So this is the this is the these are the steps by which we calculate the an. So an is basically 2 by t 0 to t by t ft cos n omega t minus ft cos omega t cos n pi t. So this an is 0 for even n. When n is even, an is 0. So only we have to find the odd terms, and this is the called 4 by t 0 to t by t ft cos n omega t dt for n odd. Similarly, we can find the value of bn. So for n even, bn is also 0. So in the case of odd, it is an and bn can be calculated for the n for odd n. Now if the function is given, how we will identify that the given function has half wave symmetry? So take the examples. If you look at the above, the first one, we can check. So this function has odd symmetry, okay, but it also has half wave symmetry. We can easily identify some sort of symmetry in first figure, but we cannot be able to identify whether this function has some sort of symmetry or not. So to check whether the given function has half wave symmetry or not, there are 4 steps. Step 1 is take the one time period of the signal. This is the first step. This is the first step. Take the one time period of the signal, okay, because ft now is equal to minus ft plus minus t by 2. So I have taken the one time period, then invert minus ft. So take this is the second step, invert the given signal ft, okay. So ft is equal to minus ft. Now inside the bracket it is plus minus t by 2. What does it mean? It means either you delayed the function by t by 2 or advance the function by t by 2. Either shift the function towards right or shift the function towards left by t by 2. So, this is the first step is take a one time period. I have taken one time period signal, then I have inverted it minus. Okay. Now, shift the function by either left or right by t by 2. It is plus minus t by 2. If you are taking minus f t minus t by 2, it means it is delayed. It is delayed by t by 2. If you are taking minus f t plus t by 2, it means the function is advanced by t by 2. So, either way, either we can shift the function either left or right by t by 2. So, this is the third step. So, third step here, it is shifted by t by 2. So, this function is shifted by t by 2, we can see here. So, this is the first step, just try to listen carefully. This is the first step, I have taken one time period. The second step is I have inverted it. Then third step is shifting the function by t by 2, either left or right, because it is plus minus t by 2, either you can shift left or you can shift the right. Now, compare this with original signal. This is your original signal, this is the after this. So, the compare the signal for one time period. This is the original signal for one time period, and this is the after the carrying out this 3-4 steps. So, we can see that these two signals are identical. It means this signal has half wave symmetry. So, particularly these type of signals where we are not able to identify where the signal has half wave symmetry or not, just take the one time period, invert it, shift by t by 2, either left or right, and then compare. This is the fourth step. Fourth step, compare with original signal. Just for the sake of clarity, I have just draw these dotted lines with the this is the take the signal for one time period, for 1t, invert the signal, we can do it, then shift either left or right by t by 2, because it is plus minus t, and they compare within the last. If these two signals are identical, then it has half wave symmetry. So, this is you have to remember this function just to check the half wave symmetry of a given signal. Now, come to the quarter wave symmetry. So, what is the definition of quarter wave symmetry? So, a function f t is said to have quarter wave symmetry if f t is equal to f minus t. So, what is this? This is basically even symmetry. This is even symmetry, and or f t is equal to minus f minus t. What is this? This is the odd symmetry. And also f t is equal to minus f t plus minus t by 2. So, this is half wave symmetry. Half wave symmetry. So, a function either having the odd symmetry or even symmetry along with half wave symmetry is called quarter wave symmetry. So, this is the definition of quarter wave symmetry. So, that is a function which has either even symmetry or odd symmetry along with half wave symmetry is called quarter wave. So there are two cases obviously from the definition. The function has even symmetry, half wave symmetry, that is case 1. If the function has odd symmetry and half wave symmetry, that is the case 2. So there are two cases associated with this quarter wave and they are discussed as. So take the case 1, it is ft is equal to minus f minus t. So it is odd and this is your half wave. So it combines, the quarter wave symmetry combines both the properties of even symmetry, odd symmetry and half wave symmetry. So it combines the both the properties. It means here A0 is 0 and AN is 0. And what we have to do? We have to calculate only Bn and Bn only for the odd harmonics. So this function will exist only if the function has quarter wave. So only one expression 8 by t 0 to t by 4 quarter period ft sin n omega t, only one expression. So basically it combines both the properties of odd symmetry and half wave symmetry. So this is the case 1. Similarly we can have the case 2. So for case 2, suppose the function has even symmetry along with the half wave symmetry. So it also combines both the properties of even symmetry and half wave symmetry. So what we will get? A0 is 0, An is 8 by t 0 to t by 4 ft cos n omega t, and Bn is 0 when n is even. So these are the properties of quarter wave symmetry. So if you are able to identify this type of property a particular signal has, your calculation will be very simple. Less number of calculations will be required to express the given function in terms of trigonometrical form of Fourier series. So all this we are going to discuss with the help of some examples. So take the examples. Now obtain the trigonometrical form of Fourier series for the waveform shown below. So if you have no idea about the waveform symmetry, what we will do? We just write the trigonometrical form of Fourier series, which is ft is equal to a0 plus summation n is equal to 1 to infinity an cos n omega t plus bn sin omega t. Then we try to find the a0 1 by t 0 to t ft dt, bn is 2 by t 0 to t ft sin n omega t dt, and an is 2 by t 0 to t ft cos n omega t dt. So you have to integrate 3 times for a0, an and bn if you are not having any idea about the waveform symmetry. If you have some idea, then calculation will be simple, less number of coefficients will be required to calculate or evaluate. So first what we will do, this is the given wave shape of a particular signal, say xt, its magnitude is a and its time period is 2 pi. So first and foremost what we have to do, we have to convert this signal into mathematical expression, then we may be able to integrate over a one time period. So first we have to write the expression for xt. So xt is, we can see the xt is minus a for a time period minus pi to 0 and it is a for 0 to pi. So if we take the time interval from minus pi to pi, so one time period, or you can take the 0 to 2 pi. So time period here is 2 pi. So we have written the expression for xt. Now this is the time period 2 pi, so omega is 2 pi by t, so omega is 1. So just look at the, suppose this is your Fourier series, trigonometrical form of Fourier series. Okay, n is equal to 1 to infinity an cos n omega t plus Bn sin n omega t. So, this omega is required. So, this omega we can get by this expression 2 pi by t. So, from the given signal, first you have to write the expression for xt, or you can say the ft, or you can say the xt. Okay. So, first write the expression for xt, then find the value of omega. So, it is coming 1. Then you check for the waveform symmetry. So, this function has odd symmetry. This function has odd symmetry. This function has also half wave symmetry. How? Look at here. The time, take the signal for one time period. Okay. Then invert the signal. Then shift the signal by t by 2, means by pi, either left or right, and compare with the original signal. So, this signal has odd symmetry, because ft is equal to minus f minus t, or xt is equal to here, xt is equal to minus x minus t. So, it has odd symmetry. If we check for the go for the half wave symmetry, it has also half wave symmetry. Half wave symmetry. If the function has odd symmetry and half wave symmetry, then it is quarter wave symmetry. Case 1 we have just discussed earlier. So, A0 is 0, N 0, straight away from the property of the odd symmetry. So, calculate the Bn, and Bn we have calculated this. So, 2 by t xt sin n omega t. Write the expression for xt here. It is 4 by 2 pi 0 to a, and this one. So, this Bn is equal to 4a upon n pi for n odd, and 0 it is for n even. So, look at here, this is the trigonometrical form of Fourier series. So, expression of the signal in terms of the Fourier series. So, it is also called the harmonic series, because this is the fundamental one, because n is equal to 1 is fundamental, and n greater than equal to 2, they are all the even and odd harmonics. So, this is fundamental, third harmonics, fifth harmonic, then seventh, then ninth. So, this way we can have the expression of Fourier series for a given signal by using the waveform symmetry. So, it is up to you, either you can use the, I have here taken the odd symmetry. You can solve this problem by using either the half wave symmetry or quarter wave symmetry. The answer will be the same. So, this is basically it is a harmonic series. So, Fourier series is also called the harmonic series. Thank you very much. Thank you.